This presentation is delivered by the Stanford Center for Professional Development.
Hey everyone, welcome. I actually have one hand up free today, and Ryan just walked in with it, so he's going to be passing it around to the people who are in the room. Remember, we have a special discussion section today at, I'm forgetting what time it is. What did I say, 1:15? I have to check. Whatever I said on Wednesday. What did I say? 2:15. Okay, I don't know why I'm forgetting. 2:15 to 3:05 in Skilling 191. We're having a special discussion section just this 1 week because I want some example problems to sit in front of you and for you to think about them more than 2 days before the next assignment deadline, which is why I'm having it today. It's going to be videotaped. I'm going to actually call SCPD after lecture today and try and make sure that they post it by 5 o'clock today so it's around for the weekend online so you can watch it. But I've already, I think, pretty well advertised that assignment 4, I think, to be kind of the biggest surprise in terms of workload and difficulty for most students. So that's why I'm kind of advertising it now to be something you want to start on sooner than later. Because if you start next Thursday, it's very likely you will not finish on time. So just try and take a stab at it a little bit ahead of time this time. When I left you last time, I had shown you two examples of how function call and return works in general, but specifically in our assembly language. So what I want to do is I want to do one specific example, actually much even simpler than the last example I did, because I want to make a transition from C code generation to C++ code generation and show you just how similar the two languages ultimately end up looking like when they compile to assembly code. So let's deal with this scenario. A void function. I just want to say foo, and I'll concern myself with the allocation of two local variables. I'll set x equal to 11, I'll set y equal to 17, and then I'm going to call this swap function. This time I'm interested in writing swap to show you what the assembly code looks like. And I think you'll be surprised to see how the pointer version of swap and the reference version of swap look exactly the same. But the way I'm writing it right now, this is pure C code. Actually, you can call it C++ code for that matter. And then that's all I want to do. I just want you to understand how code for this would be generated. I don't have any parameters whatsoever. So I would expect the stack pointer right there, to have the safe PC associated with whatever function happens to be calling foo right here. There's a call foo instruction in someone else's assembly stream, and that safe PC is the address of the instruction that comes directly after that. That's the trail of popcorn I was talking about on Wednesday. The first thing that'll happen is that this thing will actually make space for its two locals. I actually like getting in the habit of kind of taking care of my deallocation call right away. That makes sense to people? Okay. Well, as soon as I write that, I just want to remember, so I don't forget to put it on the page, to put the balancing SP change at the bottom of the stream. Now I'll concern myself with this right here. This brings this down to introduce those 8 bytes. X is above Y. So this instruction right there translates to m of sp plus 4 is equal to 11. Then m of sp is equal to 17. And then virtually all of the rest is associated with the work that's necessary to set up a function call and react to its return. Okay? So what I want to do here is I want to evaluate ampersand of x and ampersand of y. The fact that there is an 11 here, whoops, an 11 there and a 17 is really immaterial to the evaluation of these two things right here. This, given that setup right there, is synonymous with PC plus 4. This is synonymous with PC. Okay, I want to put those values in registers. R1 is equal to SP. I'm sorry, that's right. SP. R2 is equal to SP plus 4. This is ampersand of y. This is ampersand of x. I want to further decrement the stack pointer by -8. The fact that this is -8 is just a coincidence with that being -8. There happened to be two 4-byte parameters being passed here. There were two 4-byte parameters, two 4-byte locals local to foo. Once I've done that, I've decremented this by 4 more bytes. That marks the bottom of the foo activation record. I'm now building a partial activation record for the swap function. I want to lay this as a figure right there. This as a figure right there. This first parameter, the 0th parameter, actually goes at the bottom. So I want to do this. M of SP, what's just changed, is equal to R2. M of SP plus 4 is equal to R1. Okay? That basically gets this right here to point to that, and this to point to that. So when we go ahead and call this swap function, we're just inferring its prototype to take 2 int stars. It just sees this. Technically, it has the addresses, the locations of the 2 ints it's going to be dealing with, but it doesn't technically know that they're right above it on the stack frame. It actually just has the addresses on their little houses that happen to be just down the block. Okay. This right here, all it has to do is basically clean up the parameters. When the call swap function happens, PC is pointing right there. It can, by protocol, assume that that's where the safe PC is left. I'm sorry, the stack pointer is left when it jumps back to this instruction, because the return at the end of the swap is responsible for bringing it all the way back up here, just by protocol. Does that make sense? Okay. So all I need to do, fill in the space. This balances that, that balances that. You could coalesce these to one statement if you wanted to. I just don't see a compelling reason to. And then, since there's nothing being done with the new values of x and y, I can just return. Okay? Does that make sense to people? As far as the code for swap is concerned, this is a void swap. I'll write it to be int star specific. AP int star BP int temp is equal to asterisk AP. There's actually a little bit of work here at the assembly code level. I know you've seen this implementation probably 40 times in the last 2 quarters, but there's some value in actually seeing it one final time and for me to generate assembly code for it. It starts executing with the assumption that SP is pointing to a saved PC. In this particular example, it happens to be that address right there that's the saved PC. This is internally referred to as AP, BP. It's not like the words AP and BP are written on the hardware, but there's just, the code is generated in such a way that AP is always synonymous at the moment with SP plus 4, and BP is synonymous with SP plus 8, okay? At the moment the stack pointer points right there, I have to make space for my one local variable. That happens because I do this. I'll make it clear that this is associated with the label swap that we actually call or jump to. That brings this down here. This is locally referred to as temp in the code. This is the space that corresponds to temp in the activation record. The offsets of AP and BP actually shift a little bit. Now this is at address SP plus 8, SP plus 12. I have to rely on these things pointing to real data. I don't need to know where that data is to write the correct assembly code. I need to evaluate AP and then what AP points to. So as part of initializing that right there, I have to load into a register M of SP plus 8. Do you understand that it lifts this bit pattern right there and places it in a register? So I can basically do a cascade of dereferences. Does that make sense to people? Okay. Now I have AP in a register. I can do this. And now I have the very integer that is addressed by this AP thing, okay, sitting inside R2. You may ask whether or not you can do something like this. Conceptually, of course you can do that, except you're not going to find an architecture that supports a double cascade in a single assembly code instruction. Okay, so that's why they're broken up over several lines. So let's assume that this points to that right there. That's the integer that has to be loaded into temp. That's only going to happen because I do this. Whoops. And that ends this line right here. Does that make sense to people? Yeah, go ahead.
When you say R2 equals M R of R1,
Right.
why does it not just copy the address inside AP and actually dereference it?
Well, the memory of, you basically go inside an array of bytes that's base addressed right there. Okay, so you think about the entire array of bytes that's in RAM as being indexed from position 0, and so when you put that number inside, it actually goes to that address. We know that SP plus 8, this right here, we know that the 4-byte bit pattern that resides there is actually the raw address of some integer. The assembly code doesn't know that, but we do. So we're asking it to shovel around a 4-byte figure and put it into this temp variable, right? This loads that address. This address right here, let's say it's address 4000. I just loaded a 4000 into R1. Maybe it's the case that the 17 is at address 4000. Okay, that would make sense. So by effectively doing M of R1, in this particular case, I'm doing M of 4000 because that's what R1 evaluates to. Okay, and by default, we always deal with 4-byte transfers. Okay, so this would get a 17 to play the role of happy face and would put a 17 right there. Does that make sense? Okay, so now what has to happen is something similar. I have to do this right here, but it's actually a little different than this line right here because I have to find the L value by actually following a pointer. The L value being temp is directly on the stack frame in this case, right? The space where the new value is being written is actually one hop off of the stack frame, okay? Let me evaluate asterisk BP first, because it's very similar. I will do R1 is equal to M of SP plus 12. That loads just the value of BP, because that's what's stored as a variable on the stack frame, okay? In R2, I'll do M of R1, but R1 has a different value this time. Maybe it is the flat emoticon. Okay, and that gets loaded into the R2 register. That's what actually has to be written over this smiley face right there. Make sense? So in order for that to happen, I have to load this again. R3 is equal to M of SP plus 8. And I don't want to load M of R3 because I don't care about the old value. I want to actually set M of R3 equal to R2. Okay, does that sit well with everybody? Just making sure I did that right. Yeah, AP right there. Okay, make a sense? The last line is actually very similar to the first one. I know that temp is sitting right at the base of the entire activation record. Now what I have to do is I have to load the address associated with BP into R2. That's stored at M of SP plus 12. And then I have to do M of R2. M of R2 is equal to R1. That realizes this right here. So in those 3 blocks, I've achieved the algorithm that is the rotation of these 2 byte patterns actually through a third. Right before I finish up here, I have to do an SP is equal to SP plus 4. Internally, I have to bring the stack pointer up to the place where it was before I executed any code for this function. Okay? That means that SP is now pointing to the safe PC, which is perfect because in response to this return instruction, our return actually knows just procedurally to go ahead and pull that value out, populate it with place it into the real PC register, and simultaneously, or just after that, bring this back up to there. Okay? That's exactly where the SP pointer was pointing before that call statement. Does that make sense? Okay. So I went through that exhaustively because pointers are still mysterious for some people, and understandably because they're difficult. So if you start to understand them at the hardware level, you have some idea as to what the pointers are trying to achieve. They really are raw locations of figures being moved around or at least manipulated. Okay? What I want to do now is I want to show you what the activation record and the function call and return mechanisms would be for the C++ version of swap. This is very close. I'll write it again and leave it as an open question for about 2 minutes as to what the activation record must look like. I'll just do A, int, ampersand, B. So just pretend that we're dealing with pure C, except that we've integrated the reference feature from C++. Okay? Int temp is equal to, what did I say over there? A. Then A is equal to B. And then B is equal to temp. Algorithmically, it looks similar, and it even sort of has the same side effect. But you may question how things are actually working behind the scenes in order to swap things by reference as opposed to by exposed address. Let me draw the activation record for you. This is the thing that's referred to as A. This is the thing that's referred to as B. This is always below that. That's just the rule for parameters to a function or a method call. There's a save PC right here, pointing to the instruction that comes right after the call to the swap function. And then ultimately, the very first instruction does an SP is equal to SP minus 4, so that this is the entire activation record that is in place before swap actually does anything in terms of byte moving around. Okay? This A and this B, just because we refer to them as if they're direct integers, doesn't mean that behind the scenes they have to actually be real integers. The way the way references work is that they are basically just automatically dereferenced pointers. Okay, so without writing assembly code for this, when I do this and I do this, just because I'm passing in x and y, that's the way you're familiar with a swap function from 106b and 106x. Just because you're not putting the ampersands in front of those x's and y's doesn't mean the compiler is blocked from passing their addresses. This right here has to be an L value. This has to be an L value as well. It means it actually has to name a space in memory, okay, that can be involved in an update or an exchange by reference. When this right here is compiled to cs107 assembly language, it actually does exactly the same thing that does right there. C++ would say, oh, this is x and y, but I'm not supposed to evaluate x and y because I can tell from the prototype that they're being evaluated, they're being passed by reference. So the way it does it is it on your behalf, just secretly, says, okay, they really need this x and this y to be updated in response to the swap call. That's only going to happen if this is a function knows where x and y are. Okay? So the illusion is that A and B, as standalone integers, are second names for what was originally referred to as x and y. Behind the scenes, what happens is that this lays down a pointer, and this lays down a pointer. You don't have to use the word pointer to understand references. You can just say it's magic, and somehow it actually does update the original values. It lays down the address of these things. The assembly code that is generated for this function right here understands, even though you don't necessarily know this, it understands that it's passing around pointers wherever references are expected. And so it automatically does the dereferencing of the raw pointers that implement those references for you. The assembly code for this function is exactly the same as this. Like down to the instruction, down to the offsets, everything is exactly the same. Okay, do you understand how that's possible? Just because you don't put ampersands in there doesn't leave the compiler clueless, because it knows that from the prototype that it's expecting references. It's just this second flavor of actually passing things around by address. You're just not required to deal with the ampersands and the asterisks. Okay, it knows, because of the way you declared these, that every time you refer to A and B in the code, that you're really referring to whatever's accessible from the address that's stored inside the space for A. Okay, does that sit well with everybody? Okay, that's good. So people freaked out a little bit on assignment 1, I think, or assignment 2, when they saw local variables declared as references. Like, you're used to the whole parameter being a reference, as if this data type and that data type, that you're only allowed to put them in parameter lists. That's just not true. If you want to do this, if you do this right here, then that's just traditional allocation of a second variable that happens to be initialized to the x variable, or I'm sorry, to whatever x evaluates to. Okay, and that's just normal. If you want to do this, you can. Okay, and this isn't a very compelling reason, because ints are small and there's no real algorithm attached to this code, so you're not necessarily clear why I would do that. The way this is set up is that x really is set aside as an integer with a 17, y is really set aside with its own copy of the 17, but z is declared. You drew them in 106b and 106x this way. And the picture is totally relevant to the actual compilation measures, because it really does associate the address of y inside the space that's set aside for z. Okay, does that make sense? If I were to do this, you would totally draw that without the shaded box, right? This and this, from an assembly code standpoint, are precisely the same. At the C and C++ language level, you're required to put the explicit asterisks in here. You're not there, okay? You may say, well, why would I ever use actual pointers if references just become pointers? Well, references are convenient in the sense that they give the illusion of second names for original figures that are declared elsewhere. The thing is, with references, you can't rebind the references to new L values. Do you understand what I mean when I say that? It's a technical way of saying you can't reassociate Z with X as opposed to Y. Once it's bound as a reference to another space, that's in place forever. So you don't have the flexibility to change what the arrow, where the arrow points to. You do have that ability with raw pointers. So you could not very easily build a linked list if you just had references. Does that make sense to people? Okay, so that's why the pointer still has utility even in C++. Okay. You saw a method where, I think it was like get last player or something like that. There was some method in one of the classes for assignments 1 and 2 that returned a reference. And people were like, I've never seen that before. What does that mean? All it's doing is it's returning a pointer behind the scenes, okay? And you don't have to deal with it that way. You can just actually assume that it's returning a real string as opposed to a string star, or an int as opposed to an int star, and just deal with it like that. But behind the scenes, it's really referring to an int or a string that resides elsewhere. Does that make sense to people? Yes, no? Okay. So even though in C, when you C++, you start dealing with references, it's not like the compilation efforts that are in place. And the assembly code that's generated is fundamentally different in the way it supports function call and return and just code execution. Okay? It just has a different language semantic at the C++ level that happens to be realized similarly at the assembly code level. Okay? References are the one addition to C++. No, I'm sorry, there's a few, but there are a lot of people, when they program in C++, they actually program in C, where they just happen to use objects and references. They don't use inheritance. They don't necessarily use templates all that often, although most of the time they do, but that's not an object-oriented issue. They don't use inheritance. They don't use a lot of the clever little C++isms that happen to be in there. They really just code in C with references and objects. And they just think of references as more convenient pointers, less confusing. And they think of objects as structs that happen to have methods defined inside. Does that mean those are reasonable analogies I'm throwing by everybody, I'm assuming? Okay. Well, when you program as an OO purist, you're not supposed to think of objects as structs. You're supposed to think of them as these alive entities that actually are self-maintaining, and you communicate with them through the series of instructions that you know that they respond to because you read the .h file. Okay. Turns out that structs and classes, just looking at this from an under-the-hood perspective, structs and classes are laid down in memory virtually exactly the same way. Not even virtually, exactly the same way. Okay. In C++, structs can have methods. I'm not misusing a word there. Structs can have constructors, destructors, and methods, as can classes. Classes aren't required to have any methods. The only difference between structs and classes in C++ is that the default access modifier for classes is private, and the default access modifier for structs is public. Does that make sense to people? Okay. The compiler actually views them as more or less the same thing. It's just that there's a little bit of basically a switch statement at the beginning where it says, was it declared as a struct or a class? And then it says, okay, it's either private or public by default. Okay. When you do something like this, class, I'll just say, I'll just do Binky. And I'll worry about the public section in a second. Let's not worry about constructors or destructors. They're interesting, but they're just complicated, so I want to blow them off for a minute. And then privately, let's say that I have an int called Winky, a car star called Blinky, and let's say I have a wedged character array of size 8 called Slinky. And let's just get all these semicolons to look like semicolons. And that is it. And those are the only data fields I push inside. Every single time you declare one of these Binky records or Binky objects, you do this. It shouldn't be that alarming that you really get a blob of memory that packs all the memory needed for these 3 fields into one rectangle. And it uses exactly the same layout rules. Because of all the fields, Winky is declared before whatever I called it, Blinky, and then on top of that is an array of 8 characters called Slinky. That this entire thing is the B type. It's laid out that way because if you just look at this and think of it as a struct, the layout rules are exactly the same. Winky is stacked at offset 0, this is stacked on top of that, and this resides on top. This is an exposed pointer, which is why there's 4 bytes for that rectangle. This is an array that's wedged inside the struct/class, which is why it looks like that for the upper 50% of it. When you do something like this, forget about constructors, let's just invent a method right here. Let's just assume that I have this method, int, and some other thing, donkey, where I pass in, let's say just an int is fine, x, and an int y. Okay, and let me actually declare another method, car star. I'm running out of consonants. Minky. And all I want to do is I want to pass in, I'll say an int star called z, and I will inline the implementation of this thing to do this. Int y, I don't want to do that. Int w is equal to asterisk z, and then I want to return slinky plus whatever I get by calling this donkey method. I'm not going to implement all the code for this, but I will do this. Winky, winky, and that's going to be good enough. It's a very short method. You don't normally inline it in the .h. I'm just putting all the code in one board. Okay. Just look at this from an implementation standpoint, and let me ask something I know you know the answer to. Z right there is explicitly passed in as a parameter. W is some local variable, okay? That's clearly going to be part of the activation record for this Minky thing. Why does it have access to Winky right there, or Slinky right there? Because you know that it has the address of the object that's being operated on. Does that make sense? The this pointer is always passed around as the -1th argument, or the 0th argument where everything is slided over to make space for the this pointer. It's always implicitly passed on your behalf. Okay? Do you know how for like vector new and vector dispose and vector nth and vector append, you always pass in the address of the relevant struct as the explicit 0th parameter? Okay, well, they just don't bother being explicit about it in C++ because if they know you're using this type of if you're using that type of notation, you're really dealing with object orientation. What really happens on your behalf is that it basically calls the Minky function not with one variable, but with two. It actually passes the address of something that has to be a Binky class or a Binky struct as the 0th argument. So whenever you see this in C++, what's really happening is that it's doing this. It's calling the Minky function, passing in the ampersand of b and the ampersand of n. Okay, that happens to be an elaborately named function, and I'm just going with the namespacing to make it clear that Minky is defined inside Binky. Okay? And I'm writing it this way because even though we don't call it using we don't call it using this structure right here, this is precisely how it's called at the assembly code level. Okay? There's certainly an address of the first assembly code instruction that has anything to do with the allocation of this W variable. There's going to be an SP is equal to SP minus 4 at the top of the assembly code that gets emitted on behalf of this. People believe that, I'm assuming? Yes, no? Okay. The reason that C++ compilers can just be augmented, at least the code emission port of it, can be augmented to really accommodate some parts of C++ fairly easily. References and traditional method calls against an object is that whenever it sees this, it says, okay, I know they mean this because they're being all OO about it, but they're really calling a block of code, okay, associated with the Minky function inside the Minky class, and I have to not only pass in ampersand of n as an explicit argument, but before that I have to splice in the address of the receiving object. Does that make sense? Okay, so the activation record that exists on behalf of any normal method inside a class, it always has one more parameter than you think. But it still is going to have a safe PC. I'll write it right there. It's going to have two parameters on top of it. This right there, this would be the thing that is locally referred to as Z. Okay. Below that, it would make space for this variable type int called W. This right here might point to something like that. It certainly would point to something like that in this scenario right here. Does that make sense to people? Because n, I'm not using pure stack frame picture here, but because n is declared with a 17 right there, this would obviously be declared and initialized that way. Okay? Makes sense? This would point to some assembly code instruction associated with after that call right there. So there's a little bit more to keep track of, but as long as you just understand that k argument methods, k just being some number, K-argument methods really are just like K+1 argument functions. Okay? When we're thinking in terms of a paradigm, we don't actually wonder about how C and C++ are similar, but when we have to write assembly code for something, we say, okay, well, I want to use the same code emission scheme for both C structs with functions and C++ objects with methods. You can use exactly the same scheme, the same memory model for structs and classes and function call and return by just looking at K-argument methods as if they're K+1 argument functions, knowing that the 0th argument always becomes the address of the relevant object. Okay? Does that make sense to people? When this ultimately calls this function right here, you understand that it's really equivalent to that. We just don't bother putting in the this pointer. Does that make sense? So internally, when I set up function call or assembly code to actually jump to the Binky : Dunkey method, I actually have to make space for 12 bytes of parameters. 8 bytes for 2 copies of Winky, make sense? And also the this pointer. And because there's nothing in front of this, this method call, it just knows to propagate whatever value this is and replicate it down here for the second method call that comes within the first one. Does that sit well with everybody? Okay. Had I had a variable of type Binky reference here, then, and I had done, like, so let's say I had done this. I can't change the picture, but I'm just improvising this one point. If I had done something like this, Binky D, Binky reference D, and done this, then the address of whatever Binky object D refers to would have to be the thing that's laid down in the this portion of the activation record for the Dunkey method. Okay? Does that make sense to everybody? Yes, no? Got a nod? You gotta tell me. Okay. So even though you think you're data-centric when you program in C++ and you're verb, function, or procedure-centric when you're programming in C, the compilers really see them as just different syntaxes for exactly the same thing. Okay? And they ultimately become this stream of assembly code instructions that just get executed in sequence with occasional jumps and returns back. And it's just promises, because the compiler makes sure that it can meet the promise, it just promises to emulate what the C, procedural C, or the object-oriented C++ programmer intended to do. Okay? Make sense? Yeah?
So you use a method, you state it.
That's completely different. We don't see static methods too much in 106 and 107. You know how the word static seems to have like 75 different meanings? Well, it has a 76th meaning whenever the word static decorates the definition of a method inside a class. Okay, I can go over this. Suppose I have a class called fraction. Okay, and publicly I have a constructor fraction where I pass in an int n and an int denom, and I might even default the denominator to be 1, so you can actually initialize fractions to be pure integers. And I have this whole stream of methods. But then I also have this one method inside called reduce, which is intended to take a fraction that's stored as 8/4 and bring it down to 2/1. Does that make sense to people? Well, as part of that, typically what happens is that you'll write some function int greatest common divisor, int x and int y, and you'll scope it inside the fraction class because it seems it might only be relevant to your fraction class. And you actually pass in these two parameters, and it really just behaves as a function because it doesn't need the this pointer in order to compute the greatest common divisor that goes into x and y. So a lot of times what you'll do is you'll mark it as static. And what that means in the context of a C++ class is that you don't need an instance of the class to actually invoke it. You can actually just invoke it as a standalone function. In fact, it really is a regular function that happens to be scoped inside the definition of a class as if the class is a namespace around it. This is, I didn't mean to put public here. I meant to put private. You remember how on, this is how similar static methods and functions really are. Remember in assignment 2, some of you had that headache of trying to pass in a method pointer to bsearch when it actually had to be a function pointer, and you're all like, what's the difference? They're the same to me. Static methods, because they don't have this invisible this pointer being passed around, they really are internally recognized as regular functions. So if I wanted to define my actor compare function, not as a function, but as a static method inside, I could have done that. And I could have passed the address of a static function to bsearch. Does that make sense? Static method, I meant. Okay. Good? Okay. So static, I don't want to say you should avoid it. There are certainly places where static is usually a good thing to do. It interferes with your ability to use inheritance when you're dealing with C and C++. You don't get inheritance, and you don't get the right thing in terms of inheritance when you're dealing with static methods, which is why you don't see them as often. And normally when things are written as methods inside a class like this, it's because they are actions against objects as opposed to actions on behalf of the class like this would be right here. Okay? Any other questions? Okay, so next Tuesday, when we pick up on the normal discussion section cycle, you will get a section handout where you'll have some elaborate, well, I don't want to say elaborate, some meaty examples on C and C++ code generation. I'm only going to test you on C code generation with no objects and no references on the midterm, although it'll be fair game on the final. Next Wednesday, I will give out assignment 5. It will not be a programming assignment. It'll be a written problem set where you're not required to hand it in. You're just required to do it and make sure that your answers sync up with the answers that I give out in the key. And it'll totally be testable material, and you're just required to effectively do it by 6:59 on Wednesday, May 7th. Okay? Does that make sense? So you have a full week to do this one assignment, which means you'll all do it on Tuesday, May 6th. But you'll have a week to actually kind of recover from the assignment 4 experience and learn all the pointer stuff. Okay? Does it make sense? What I want to do is I want to start talking a little bit about how compilation and linking works. We completely disguise compilation and linking with this one word called make. And it's like this magic verb, like just do it and make it work for me. And somehow it actually usually does do that for us. But when you compile C code, C++ code as well, but C code I'll focus on, it normally invokes the preprocessor, which is dedicated to just dealing with pound defines and pound includes. Then it invokes what is truly called the compiler. That's what's responsible for taking your .c files and your .cc files and generating all those .o files that happen to appear in your directory after you type make. Make sense? And then after compilation, there's this one thing you don't think about because CodeWarrior and Xcode and Visual Studio C++, they all make compilation look like it's the full effort to create an executable. But once all those .o files are created, and one of the .o files has code for the main function inside, there is this step called linking, which is responsible for taking a list of .o files, stacking them on top of one another, making sure that any function call that could possibly ever happen during execution is accounted for because there's code for that function in one of the .o files, and then it just wraps a.out or 6 degrees or my executable or whatever you want to call it around the bundle of all of those .o files. Does that make sense? Okay, somebody mentioned the other day that a line like this, why wouldn't it be replaced by call of like PC plus 480 or PC minus 1760 to actually jump to the actual PC relative address where the swap function starts? That actually will happen in response to the linking phase because everything's supposed to be available to build the executable file. And so if it knows where everything is in every single .o file, and it knows how they're being stacked one on top of one another, they can replace things like this with their PC relative addresses. Maybe at the time that things are linked together, it knows that the swap function happens to be the one defined right above this. So when it calls swap, it actually calls PC minus, let's say, 96 or something like that. Okay? Make sense? Okay. Let me get some clean board space and just spend 5 minutes, that's all I'll be able to do, really, talking about the preprocessor. And I'm doing, okay, I have 5 minutes. Whenever you dealing with pure C, if you want to declare global constants, traditionally, until recently, you only had pound defined as the option for defining nice, meaningful top-level names for these magic numbers or these magic strings. So something like this, pound defined, I'll just do K width. Let's say it's 480 pixels, so I write down 480. And then I have something like this, K height, 720. And then I have some pound includes, I'll talk about those later. And then there's all this code right here where usually it's the case that some part of it is framed in terms of that and or that. So maybe it's the case that you have a printf statement. Width is %d \n. Oops, right there. And then you feed it the value of k width. Maybe a more meaningful thing might be something like int area is equal to k width times k height. And it exists in your code somewhere. When you feed, or when a .c file is fed to GCC or G++, there is a component of either GCC or G++ called the preprocessor that doesn't do very much in terms of compilation. It doesn't do compilation as you know it. It actually reads the .c file that's fed to it from top to bottom, left to right, like we would read a page. And every time it sees a pound define, it really only pays attention to these words. What it'll normally do is it'll read in a line, and if there's nothing that has a hash at the beginning of the line, so it doesn't involve any pound defines or pound includes, it'll just say, okay, I just read this one line and I don't care about it. So I'm just going to publish it again as part of my output. When it reads something like this, it internally has something like a hash set, although it's probably, I don't want to say it's strongly, but it is probably strongly typed. It associates this as a key with this string of text. It doesn't even really know that it's a number. Okay, it just says everything between the white space that comes right after width and the white space that comes after the first token, that's associated as a text stream with that identifier right there. Okay, does the same thing for that right there. And as the preprocessor continues to read, every time it finds either that or that in your code, the one exception being with inside a string constant, but everywhere else, it says, okay, well, when I see that, they really meant that number right there. So it lays down 480 as if you typed it there explicitly. Does that make sense? Okay. You know the alternative would be to put lots of 480s all over the code base without using a pound define, or lots of 720s around the code base without using a pound define, but then you change the dimensions of your rectangle in your graphics program or whatever, and then you have to go through and search and replace all the 480s to make them 520s or whatever. It makes some sense to consolidate that 480 to a pound define if the pound define is the only thing that is available to you. But the pound define is really very little more than pure token search and replace. Okay? Does that make sense to everybody? So the responsibility of the preprocessor is to read in a .c file and to actually output the same .c file where all the pound defines and other things like pound includes have been stripped out, and the side effects that come with pound defines have been implanted into the output. So this right here would it would be missing these two lines. Anything that's right here that doesn't involve those two pound defines would be output verbatim. This one line would be output verbatim, except that would have a 480 replaced right there. Okay, and this right here would have to, and that right there, it would probably have a 480 times 720, although the compiler might actually do the multiplication for you if it's a very good compiler. Okay, does that make sense? Actually, I'm sorry, the preprocessor would not do that though. This would just become 480 times 720. Okay, and the fact that it happens to be text, it is really text at the moment. It's just that when it's fed to the next phase of compilation, it'll go ahead and it'll chew on those things and recognize that they really are numbers, and that's when it might do the multiplication. Yeah?
If you have a pound define of k-width, and then you declare a variable called like k-width underscore second or whatever?
Yeah, it won't do that. It has to be recognized as a standalone token. So if I did this, for instance, like kwidth _2, something like that, it'll not do subtoken replacement for you. It also won't do it within string constants either. Okay? Okay. I'm not done with the preprocessor yet, but I can certainly answer your question. Go ahead.
When you describe printf,
Yeah.
what is the preprocessor do with that line?
Preprocessor would basically output this line right here, except the kwidth would have been spliced out and replaced with the 480. Okay? Which, I mean, it's supposed to be functionally equivalent. It's just allowing for the consolidation of magic numbers and constants, or whatever we want to use with pound defines for, to just consolidate all this information at the top. Okay? Yep?
Preprocessor.
It actually does not know that 480 is a number yet. They just are incidentally digit characters, and that's it. But if I had done this, like that right there, the preprocessor would be like, okay, I'm just going to take that 6-character string and put it right there and right there. And it's only later on, during real compilation, post-preprocessor, that'll be like, hey, you can't do that. Okay? Does that make sense? Okay. But that wouldn't happen. Okay, so come Monday, I will finish up the preprocessor. Pound defines are easy. Pound includes are not. There are actually some involved with that. And then I'll talk about compilation and linking. Okay, I will see you on Monday.